What are coordinates? How does coordinate transformation work and why it is so important? The fascinating thing about coordinate transformations is that they allow us to express the same physical phenomena in different ways without changing its essence. It is just like telling the same story in multiple languages, yet the story's meaning remains the same. The invariance is a powerful concept in physics and mathematics. Welcome back to this series on tensor calculus, and this is the lesson 2 of this series which we are continuing, and today we will explore how to perform a basic coordinate transformation and demonstrate how measurements remain invariant despite the change in perspective. Don't worry, I'm going to take a beginner friendly and an easy to follow approach. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to lesson 2 on tensor fundamentals. Before we go ahead, start and go deep into the mathematics, here is a quick recap on the ideas and the important topics that we covered in the last video. However, I am putting it in the I button. You can go ahead and check because that is the foundation and that contains a fascinating history and very important facts on tensors. So what we covered is that what is a tensor, and we understood that it is derived from the Latin word tender, which means to stretch. It comes from anatomy, that is a muscle that tightens and stretches and pulls. We also showed that if there is a sphere and there is some kind of data over here, then it gets transferred into an oblate spheroid. The data gets stretched out. So how will we come to know about this stretched information? That means we can tell that tensors somehow stores stretched information. So here is a easy definition. It is a set of components functions that transform linearly between coordinate system. And why linearly, why coordinate system? You can check out my first video which explains on that. The second thing we saw that there are certain important features which makes tensors very important. Among that, first was that it has a Rankine order, it also has a shape, it has different types of components, and most importantly it has got transformation rules, and we are going to explore what those transformation rules and how we can mathematically derive and show it. So these are the few important features of a tensor. We also saw that in terms of transformation rules, if we get a Cartesian flat coordinate and we get a here kind of a curvilinear coordinate, our data over here gets stretched over data over there. So we actually move from flat space to curved space. Similarly, a sphere, when it is stretched, it becomes an oblate spheroid. So our data over here gets stretched or data over there. So the object is stretched. Similarly, when we see a Cartesian coordinate rotated, so the data gets rotated from one place to another. So what do we see is that how do we measure things, and tensors helps us to keep the measurement invariant in spite of the change of coordinates. And this is what is the basic tenet of physics, that we need to know that the laws of nature should be invariant under any coordinate transformation. We also explained in the last video that tensors actually started with the study of crystals, because crystals comes in different dimensions, shapes, sizes, etc. So if we try to plot the size of crystals, they become very complex, and with the help of vectors it is not possible. So we need what is called tensors. So it has got many faces and directions, and now it is important not about the direction but also on which plane it is occurring. We also saw a brief history which started with Augustin Louis Cauchy on the Cauchy stress tensor, extending to William Rowan Hamilton, Bernhard Riemann, Joshua Willard Gibbs, and to Ricci tensor, and further on, which you can check out in the first video. We also broke the myth that is it Einstein who discovered tensor calculus, and I showed historical evidence and manuscripts which proved the fact that it was not Einstein but somebody else. Who was that? In order to watch that, go ahead and watch the first video on that. Now, taking all those things, which is a quick recap, what we understand is that it deals some with coordinates and system transformation. This is the video, just a thumbnail I have given. You can go and watch it. Now, because everything deals with transformation of coordinates, etc., so now we need to explore a little bit more after having laid the foundation of tensor history and the basic understanding. What are the coordinate system and how does it transform? Let us look in the next part of our video. So here we will start with what is called a coordinate system transformation. Now you see that in the earlier video I have expressed this typical I would say example. A person is throwing a ball in one coordinate system and the same person is throwing the ball in another coordinate system when I rotate the axis, and I'm going to take this example, I'm going to explore it further. Now events as we measure in physics should be same in all frames of reference. So whether the person is throwing the ball in a flat space or it is in an extended Cartesian coordinate where x and y are more, the events has to be measured in the same, and that is the idea of tensors. So here the straight line, which is technically called geodesic, get extended further into an oblate spheroid. Still the measurement should be the same, and we saw that what Einstein actually quoted in his famous line, that the general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. So this is the basic idea of Einstein. This is the basic idea of general relativity and to the all parts of physics, that the rotation transformation of coordinates should not affect the basic measurement system. So we are going to take ahead and we are going to explore on that. So first what I would like to tell you is that the vector concepts that we saw earlier actually are quite useful to describe. One, it helps to solve a wide range of problems in physics and engineering, and two, they provide a foundation of understanding of tensors. This we have already understood. Now to achieve the understanding, we have to move beyond the simple definition that vectors are just objects with magnitude and direction. Instead we have to think that vectors are objects and components that transform between coordinate system in a specific predictable manner. So vectors can have more than one kind of a component, and those different kinds of components are defined by their behavior. So here you see I have written that it is important to realize that vectors can have more than one components, and the objects with components that transform between coordinate system behaves in a specific predictable way. Now whenever I say it is specific predictable, I am trying to define a specific set of rules. And this is the set of rules which actually is the pivotal force which rules up the tensor. In order to know that, we have now gone and extended beyond the basic concept of vectors. It is not magnitude and direction, but it contains certain components, and we now will see that what are the specific and predictable ways in which things happen. So my first question to you would be, what happens to a vector when you change the coordinate system in which you are representing a vector? So the basic answer to this question is that nothing at all happens to the vector itself, but the vector's components may be different in the different coordinate system. And also the vector itself does not change if you change the coordinate system. So what happens to the vector? Nothing happens. The vector's component may be different, and the vector itself does not change if you change the coordinate system. Now if that is so, let me explain you with a very trivial and a simple example. Now if this is a kind of a room and we are trying to measure the temperature, whether we define the temperature in terms of centigrade or Fahrenheit, the temperature of the room will not change, only the representation will change. Here you see, whether you measure temperature in Celsius or Fahrenheit doesn't make the room feel hotter or colder. But the question is that here is a sofa, or you can say this is a kind of a room, isn't it? So now the question is that if you use your other coordinate system in order to represent this sofa or this room, how does it change? What do I mean by that, by this analogy, coming in the next part of the video? So what I have done is that I have taken this room, and here I am, and I'm watching this straight. So this blue line, which is a kind of a vector, but you can consider this to be a straight line, actually watches this room. Now what I will do is that I will tilt my head. Right? So what I'm going to do is that I'm going to tilt my head and I'm going to look at the room. So what happens? Nothing happens. The size of the room does not change. Whether I tilt my head, put it down, put it up, etc., the size of the room will not change. But if I use my tilted head to define something which is up and down, the points, the coordinates that I designate as the top, bottom, etc., that might create a change. Let us look into the example. The same room, here I am, I'm looking straight onto the roof or right on the bed, and this is the dot which is mentioning the change, mentioning the point. Now here is my tilted head. Now if I am trying to define, for example, left, right, up and down, height and width of the room by tilting my head, and then I look up to the room by pointing this arrow, you see that the point has now changed. The room has remained the same, but the point has changed. Now if I try to define the x, y and z axis, that is the height, etc., this will actually cause a change. So the important idea is that the room itself does not change. Technically we call it is invariant under such a change of coordinate system. And if you define the center of your head to be the origin of your coordinate system, which is right there on the screen, that is x, y and z values of locations within the room may change. But once again the room remain itself as unchanged. Now likewise, if I specify something, for example, whether I measure it a room in terms of inches or in terms of meter, it doesn't change. It doesn't change likewise. It doesn't make that it will hold a bigger sofa or a smaller sofa. No, it doesn't. So what it does is that the example actually explains that the changes in terms of coordinate system, in terms of inches, meter, etc., it doesn't change the basic idea of the room. So if a coordinate system's transformation such as rotation, translation and scaling leave physical quantities unchanged, what exactly happens when you transform the coordinates? Let us look in the next part of our video. So when coordinate transformation systems such as rotation, translation, etc. changes, what precisely transpires with a vector during a coordinate transformation? Here is a quick example. So you see on the left hand side, this is a simple x and y coordinate, and what I have done is that I have just rotated this. So on rotation, what happens? The location of the origin has not changed, obviously. So only what happens is that the x and y, as you can see, both the x-axis and y-axis has been tilted counterclockwise, and there is an angle which is formed, that is the theta. The rotated axes are labeled x prime and y prime, as usual we do in physics and mathematics, and are drawn using dashed lines, as you can see on the left hand side, to distinguish it from the original axis. So this is what happens. The location has not changed. It is tilted counterclockwise. There's a theta angle which has changed, and the rotated axes are labeled as x prime and y prime. Now, okay, so here is another analogy. If I take a flat surface, something like this. So here is a vector, right? And I will measure the component of the vector ay, and this right as ax. Everything is fine. We define this by the component. This is the blue line. Now I come to a curved space, and I plot the same xy, that is the Cartesian coordinate, and this kind of a curved linear face, and I measure and I mention this x to be x prime and y to be y prime. See what happens, that the vector a remains constant. Nothing has changed. But you see the lines joining, which are the components of the vector. I mean to say those who are actually making up the vector, this has become broader. So here is the summary. A prime x obviously is longer, a prime y is longer, but a will always remain invariant. If I take another example, for example, this we will further elucidate in the next part of the video. So here you see that this one ax again, and the ay is a bigger one, but if I take this one, the rotated one, you see a prime x becomes much longer and a prime y becomes much shorter. So what we see is that this is bigger and this is shorter. This is a static frame of reference, and this is the rotated frame of reference. And this is what we call, we will look into that, don't worry, we will derive actually. This is actually mentioned by using a specific tensor which is called the metric tensor in general theory of relativity. I already have a very detailed video on metric tensor, but however in this series also we are going to look more into metric tensor. So far so good. So if you think that this one, we have taken these two figures, the static and the rotated, right? And what we see is that you see that the ax contains some but not all the information about the vector a, and this contains the ax in the rotated coordinate system. I mean to say it cannot depend entirely on the ax in the original system. After all, ax contains some but not all information about the vector a, this one, and the rest depends on this one, that is the AY, which is the Y axis. And as the axis rotate, you see the axis that had point exclusively in the X direction now points partially in the former Y direction. So it seems reasonable that if I say that the portion of A that had previously pointed in the original Y direction now points in the X prime direction, and hence contributes to the X prime component as well as the Y prime component. So this is something which we need to depend, that how the dependency of the vector changes. These informations are also dependent on X and partly on Y. Why it is dependent? Because these are the components. Adding these components makes up the complete vector. Now you can see that if I take this figure, figure 1, now you see that the circle is basically a magnification of the first figure, nothing else. Now you can see that if I go for the figure 1, the portion of the figure shows that the vector component, this one, AX, now I just circled it, let me do it again, this one, I mean to say this A prime X in the rotated system, and the figure 2 portion shows the AYs in the original system contributes to the A prime X in the rotated system. So as you can see in both portions of the figure, A prime X actually can be considered to be made up of two line segments, this one highlighted in blue, the L1 and the L2. So what we can say definitely is that A prime X is a summation of L1 plus L2. I hope this is clear. So you can see the magnified version of the figure. This one, L1 and L2, it is just a projection of the vector. On figure 2 also it is a projection. So we can definitely say that the A prime X is consisting of the two lines L1 and L2. We take the next figure, and what we see is that it forms an angle. I have named it as alpha 1 1. I will tell you why, because this double script actually becomes very useful when we are using the matrix notation. Then the length L1, that is the projection of AX. This is the projection of AX onto the X prime axis. You can see AX right at the bottom, X prime on the corner. This is also, we can say L1 is what? Simple. It is AX cos of the angle alpha, or we can say alpha 1 1. Now if you take this figure, what we see from this is the triangle that we should be able to see, this one, L1 and L2. So from here what we find is that L2, the L1 we have seen, now we are watching this L2. L2 is simple, the AY component multiplied by the cos of alpha 1 2. So angle alpha 1 2 is the angle formed by the tip of A prime X and A prime Y, which is also the angle between the X prime X axis and the Y prime X axis. Fine and good. Now you see that if I take these two equations which we have just derived, L1 and L2, we can add these two expressions and get something like this. Now what happens, you see this AX and AY which I have just highlighted, these are actually the components of the vector, original vector, remember A, in the non-rotated coordinate system. So these are, because there is no prime, you can very well understand this is non-rotated system. So AX and AY, forget about the cosine part, is basically the non-rotated coordinate system, and this alpha 1 1 is the angle between the X prime axis and the between the X prime axis and the Y axis. So on the right hand side I've just given the figure so that you can understand. Here it is A prime X, A prime X, A prime X, A prime X in both the figures. So this is the non-rotated part. Now you should also note that the new component that forms that A prime X is actually called what is a weighted linear combination of the original components. Now why it is called a linear combination we will explore soon, but you see A prime X is a contribution of AX and AY. Now you might be wondering that what is weighted linear combination, although you might have seen, but here is just a quick review of what is called a weighted linear combination coming in the next part of our video. What is a weighted linear combination? I will give you a very simple example. So you see, a weighted linear combination is something we always do in mathematics. You combine several values, which can be components, variables, whatever, by multiplying each value by a specific weight, and then we sum it up. For example, if I get this one, x1, x2, x3 dot up to xn, then what we do is that weighted linear combination, I have just abbreviated as WLC, would be w1x1 plus w2x2 plus w3x3, and it would continue dot up to wnxn. So what we are doing is that we are just multiplying the value of xi by its corresponding weight wi. And then we sum up all of this, and the product that we obtain is that it is called a weighted linear combination. Now, why is that word weighted linear combination? Let us quickly look in the next part of our video. Why we call it weighted? We call it weighted because the term weighted means each value is assigned a weight. Whatever the value it is assigned a weight, and these weights determine how much values it contributes to the final result. Linear, why it is called linear? Very simple. The term linear is used because the combination is a linear operation. We can take an example in mathematics. Generally, we call a function that satisfies the properties of linearity. That means if we get two values, say a and b, and we combine them linearly, it means that the result is obtained by adding the weighted values of a and b. And why it is a combination? That is quite obvious, because ax and ay both contribute towards making up the vector or the component of the vector a prime x. So this is a quick review on weighted linear combination. Now the question is that all of these things we are seeing that with the vectors, with the lines, etc. But what about plotting some real values? What about getting really to know whether it is positive, negative, which way it is going ahead? And in order to do that, we won't use a curved coordinate. We use the simple Cartesian coordinate. But examples will show you how exactly the vectors look like, coming in the next part of our video. This is called what is called a transformation equation. Okay. So here you see in the transformation equation what we do. This is the transformation equation which we have seen, and from there we can deduce into this. And see what happens is that the first transformation equation is the a prime x. But if we do the same transformation equation with a prime y, so here it is doing analysis with the coordinate, then here is the coordinate, this is the original vectors a which is pointing outwards, we get this one. So a prime x, a prime y equal to cos of alpha 1 1, alpha 1 2, then cos of alpha 2 1, alpha 2 2, followed by the original coordinates ax and ay. So this is actually what we call is a transformation equation. Very, very central, very, very important, and we will see how this transformation equation, as I was just telling, that we can plug in the values and we can finally find out how actually the vectors look like. This part actually is called transformation matrix, and the values inside are called direction cosines. So this is just a kind of a terminology. Now let us see that if we can at all put up the values and find out how the I would say the coordinates actually look like and how do they behave, coming up in the next part of our video. You see that rotation along the Cartesian axis, this is what we are going to go ahead. So what we see is that, let us say for example we take a kind of a vector. We just take this as an example, and the vector is just 5i plus 3j. It is just for the practice because we want to see that, and we are doing it, remember, in a two-dimensional Cartesian system. Now what we were going to do is that, let us say this figure. Now imagine that the x and y axis of this particular figure of the Cartesian coordinate system is rotated here counterclockwise. It is rotated counterclockwise by an angle of 150 degrees. Now before jumping into further equation, I want to make a close understanding of this part. That is, we find the components of a prime x and a prime y. But before that, what I would like to show you is this, that you see the axis, x and y axis rotated by 150 degrees, and clearly you can see that a prime x and a prime y are negative. You can see here it is going this way and a prime y is going in this direction. Also what we can see here is that the a prime y component appears to be somewhat larger than the a prime x component. It's a kind of a quick observation. Now this is actually the transformation equation, what we have seen just now, and we are going to take this transformation equation further into this part. Now here is that you have this idea, I have just plotted it in this way, that the relevant values. Now we take the values, we take ax equal to 5, ay equals to 3, and use the angles, this one, alpha 11, 150, 160, 240 and 150 degrees. So what we have is that from the original transformation equation, we get this one, 150, 240, 60 and 150 degrees, simple, the left hand side and then the right hand side. And from here, if we can plug in those values of the vector, so 5 becomes, this one become 150 degree, 3 cos 60 becomes minus 2.8, and then we see that a prime y becomes this one. So what we have done is that you can see, just I have substituted the values in the cosines. I have put in 150, 60 and 240 and 150 degrees, that's it. And then with the help of my calculator, I've calculated these values. Now most importantly is that you see, and just if I go back, let me go back to this part, what we have just observed is that a prime x and a prime y is negative, right? And now if I go further, I will see that the values obtained over here, you see it is negative. So from the visual analysis and from the putting the values, you see that the negative and the y component is larger and the x component is x component in the rotator system, that it shows. So a prime x is minus 2.8, which is negative. A prime y is minus 5.1, and it also shows that the y component is larger because it is minus 5.1. X component, which is the transformation equation, as you can see here. So we should remember that this actually does not rotate or change the main vector a, but what it does is that it determines the values of the components of vector a. So if you now want to apply this transformation, because you might be thinking, okay, let us apply this transformation matrix to some basis vectors such as i10 and j01. So definitely you can do that, and that would be a good thing to see that if you put in these values, what actually it results into. So for I, the value would be this one, cos 150 and so on. And if I do further using 10, it would result into this and this. So we get minus 0.866 and minus 0.5. Now if I use this one, which is j, so obviously what I would use, it will be 01 instead of 10, yes. And here I get the value, and if I calculate the values, I get 0.5 minus 0.866. Now you see, the beauty is that what has happened is that we have just swiped the values 10 to 01, and you see here what happens, 1 cos 150 degrees goes to, and 1 cos 250 degrees just swipes to 0 cos 150 degrees to 0 cos 240 degrees, and 0 cos 60 degrees and 0 cos 150 degrees becomes 1 cos 60 degrees and 1 cos 150 degrees, because we have just multiplied with 0 and 1. And here also you see the values are swapped. Minus 0.86 has gone downstairs and minus 0.5 has gone upstairs. So this is something very central. Remember, these are the components of the original unit vectors, which are the non-rotated coordinate, not the rotated, but expressed in the rotated coordinate system. So it is originally the non-rotated system which is expressed in the rotated coordinate system. How the expression is done, this is right in front of you. Now let us look this as an illustration with a figure in the next part of the video. Here you can see this is actually the y component of I hat, that means the unit vector in the rotated coordinate system. This one is the x component of I hat in the rotated coordinate system. This one is the x component of j hat in rotated coordinate system, and this value is the y component of j hat in rotated coordinate system. So this makes things quite clear that how the rotation, and it is the original coordinate system, the non-rotated one, which are expressed in terms of the rotated coordinate system. So this is something which is called inverse, or we call passive transformation. These things will also become much more clearer. Now at this point you might be wondering that how you might go about transforming the unit vectors of the original, I would say, non-rotated system into the rotated. So here is something which comes up very easily. I mean to say, if you make it in a very simple manner, components of same vector in new system is equal to the inverse transformation matrix multiplied by the components of the vector in the original system. So you see the components of the same vector in the new system, which equals to the reverse transformation multiplied the components in the original system. Now what I was telling is that if you wondered that how would you go about the transformation of the unit vectors of the original non-rotated system, that is this one, that is this ij, into the rotated system, which is I hat prime and ij prime, then this transformation happens. And that means what you are asking is this one: how do you change a given vector in a different into a different vector, that is the unit vector, in a different coordinate system? So how do I change a given vector, in this case a unit vector, in a coordinate system into a different vector, that is the unit vector in a different coordinate system? This would be the answer in which I would address in the next part of the video. So till now this has been the complete understanding of the rotation, the transformation, and we denote those original non-rotated in the rotated system, in Cartesian coordinate system, how things happen and when do we put the values, how they do like that. So here is a very quick summary of what we have done today. Coordinate system transformation, we have looked into what is a rotational transformation, what is a transformation equation, which is a general transform equation, and then when we have used the transform equation using the cos and the values, etc., how does it become? And we have quickly looked into the very basic of what is called a weighted linear combination. In the next part of the video, which I would do, which will be continuation in this series, I would be basically looking into what is called basis vector transformations. That is very important, and basis vector versus component transformation. That would be the next part of the video. I'm extremely thankful for those who have watched this video. Thank you for watching, and if you have really liked this video, hit on the subscribe button to get all the notification from Physics for Students. You can always contact me at this ID. You can subscribe to my other channel related to general theory of relativity, and if you want further, you can follow me in my Instagram, in my LinkedIn, Facebook and Twitter account. That's it for today's video. This is the lesson 2, where I give you an understanding of the transformation, coordinates, how does it look like, and in the next part we are continuing with this series. We will look further into the tensor analysis and then go into further details. Thank you very much for watching this video, and I will wait for your comments. Goodbye.